Thank you very much. Thank you, Lauri, for the introduction, and thank you all for coming. So I will talk about the science of software and system design, and let me start with some general motivating words. I think it's no secret to anyone that our society these days is full of computer-controlled systems. Basically, all aspects of our life, or all sectors of our economy are dominated, and increasingly dominated, I would say, by all kinds of systems where computers play a major role, from transportation, avionics and aerospace and defense for many years now, transportation perhaps more recent, factory, industry automation, energy more and more, healthcare more and more, smart buildings, many cars, roads, many things. And this is not likely to increase. In fact, it will increase in the future. Now, when you look at these systems, these are highly complex systems. And I'm using the term complex systems here, not in the physics, weather, chaos theory, fractal sense, but in the engineering sense. And to me, there are three factors of complexity here. One is the sheer size of these systems. So your cell phone, your laptop contains chips that have billions of transistors, right? So these are numbers hard to imagine for a human being. These systems are running millions or tens of millions or even hundreds of millions of lines of code, even in unexpected places, like in your car. Your car might be running 100 million lines of software in it. So that's one thing, the size. Second thing is the software itself, the inherent complexity of the software. And I have a separate slide for this coming up. And to me, it seems that software is the most complex artifact that humans have ever built in their history. And we need to understand how complex it is. And third thing, as I said in the previous slide, this is not just about computers. This is not about computer science only anymore. These are not standalone systems. They are embedded into larger systems. They are embedded in your self-driving car. They are embedded maybe in the pacemaker that controls the heart of a patient, and many other things. So these cyber-physical interactions, cyber the computer, physical some physical environment, create interesting phenomena that we don't fully understand or control yet. But I want to focus on software for a moment, and again, talk about the inherent complexity of software. So you don't need to be a computer scientist. You don't need to be a programmer. This is a 6-line program that anybody can understand what it does, at least at the surface, right? So you get a number from the input from the user. It's an integer number. It better be greater than 1 to make things interesting. And then you test. If the number is even, so if this is divisible by 2, you divide it by 2. If it's not even, then you multiply it by 3 and you add 1. And then you repeat the process over and over and over again, until at some point maybe the number will become small enough, will become 1 or less, and then you will exit the loop and terminate. And the question now is, does this program always terminate? And it's very fun. I invite you to try this at home. Plug different numbers. You can do it on paper. Sometimes the numbers go up and down for a long time, but the program always seems to terminate. You always seems to arrive at 1. But we haven't been able to prove that. We haven't been able to prove that for all possible inputs, this program always terminates. So this is the famous collage conjecture. The conjecture is that, yes, indeed, this program always terminates, but it's an open problem in mathematics. So the best minds, the brightest mathematicians in the world cannot really solve this problem. So this is a very difficult problem, and it's only a 6-line program. Now imagine, this shows me, at least, that software, there is some inherently complex about software. Imagine this complexity now multiplied in millions or billions lines of code. So we need to deal with such things. But software, of course, is great because it enables many applications. We wouldn't be able to even be thinking about these things if it weren't for software. This is one of my favorite applications of smart or cyber-physical systems, an autonomous intersection. So imagine, in the future, a world without traffic lights, where cars just merge through an intersection, maybe without stopping, so maybe slowing down, but they don't crash. They have intelligent protocols and sensors and software that controls these things and negotiates how am I going to cross the intersection so that I don't crash with the other cars. So this is just a simulation. It comes from a project called AIM, developed at the University of Texas at Austin. This is how it might look in real life. This is actually not real, but this is just a video produced by an artist. It's very nicely done, I think. It's funny or scary, depending on your point of view. But you know, this is what might come in the future. And obviously, it's safety critical, and we want to get it right. So now, how do we design such systems? And I'm using the term design here, not in the artistic sense, but in the engineering sense. So design means from concept to development to deployment, implementation, you know, final product. And basically, there are two approaches, and they may not be as black and white as I'm presenting them here, but I'm trying, you know, to contrast them just to make my point. One approach is what I would call design by trial and error, okay? And Antti mentioned this also earlier today. So this is basically, well, you build it, you deploy it, you run it, it might fail, it might have bugs, you find mistakes, you fix them, and you try again, and again, and again, until hopefully at some point you will converge, the system will be running okay, and that's it. The other approach is more scientific, I would call it. So designing more rigorous, formal, perhaps mathematical methods. And I'll come back to those two. But design by trial and error is something that humans have been using for ages now to build all kinds of systems. And I find this video also very, very interesting. It shows the collapse of the Tacoma Narrows Bridge many, many decades ago, back in 1940. Okay, so you see the bridge oscillating in kind of amazing way and finally collapsing just a few months after it opened. So this is not really related to computers in any way, right? But it illustrates this trial and error approach. So you build the bridge collapses, back to the drawing board, what have we done wrong? How can we next time not have such a catastrophe? This is a more relevant example and more recent example as well. This is the explosion of the Ariane 5 rocket back in 1996. And this was really something due to software. So a software bug caused the rocket to self-destruct, in fact, after going out of trajectory. And this is a more recent example. This is a video that you can find on YouTube. This is about a year old, a year and a half. The Tesla autopilot, which got confused at some point and tried to steer the car in the direction of the oncoming opposite vehicle. Luckily, the driver realized, so the system also beeped, saying, oops, I don't know what I'm doing. The driver grabbed the wheel, steered the car back into the road and avoided the accident. Not all drivers have been so fortunate. About a year ago, again, this is the first recorded human casualty due to a self-driving vehicle. Again, same Tesla autopilot, the person died. Now, is this the way to go? So is trial and error the way we are going to build systems? And some people may, arguably say yes. I mean, this is how human beings have always pioneered new fields. A few people will be brave enough to try these things first. Maybe a few will die. Some sacrifices need to be made. But overall, we'll fix things, we'll get them right, and eventually, humanity will advance. And that's how things are. It may be that trial and error is the way to go. I personally think it's not the way to go, at least not the single way to go. And I think so because of software complexity. And when you look, again, at software, there's so many possibilities to get it wrong. that you cannot hope to converge simply by trial and error, deploying out the software, finding the next bug, fixing it, and deploying it again, finding the next bug, and fixing it, and so on, right? So we need something more rigorous. We need something more scientific. And scientific, science is not something that, of course, this is the first time that it appears. Humans have been using science in building all other systems as well. And bridges, and that I showed, and rockets, and so on. All these systems relied on sciences that are mature, that have been around for millennia, physics, mechanics, chemistry, many other disciplines that we understand well. And what about software? What is the science of software? Is there even a science of software? And maybe, is programming an art? It may be. Is it a science? So we are still, computer science is a new discipline and still hasn't settled this question entirely. Obviously, I believe there is a science of software, and I will come back to that. Now, the current practice, for the most part, is software testing. So we test the software. And this is really the trial and error approach, right? So we write our code, and then we run it before we deploy it. We run it again and again and again with different inputs in different scenarios, trying to find bugs. And we find the bugs, and we fix them, and so on. Now, as you can see, the larger the software becomes, the more complex our systems become, this will not scale. Okay, and indeed, it's becoming very, very costly. For every dollar that you spend writing a piece of code, you spend, I don't know how many dollars, 10 times more. I don't have the statistics, but you can find statistics that show that testing is becoming overwhelming in the cost of the overall project. And also bugs that you found that you may find late, you may find them too late after your rocket has exploded. They are harder to fix, costly to fix, and so on. Okay? So, and the final point is perhaps the most important point, is that in the end of the day, how can you be sure? And as Dijkstra, one of the fathers of our field, said many, many years ago, testing can show the presence but not the absence of bugs. So in the end of the day, even after all the testing you have done, you can never be sure. You can never sleep in peace, let's say. So what's the alternative? And this is what I would call the science of software and maybe even system design. The alternative is an area called formal methods, and this is the area that I represent and advocate here. These are mathematical methods. They are typically based on logic, and by logic I mean both classic mathematical logic, but also many, many different other kinds of logics that are developed every day. They are tailored to particular applications and serve and give rise to tools targeted at those applications. And to contrast this to testing, the main problem that we are trying to solve, or at least one of the main problems that we are trying to solve in this area, is the problem of verification, where we try really to prove that the system, the software, or whatever it is, will work correctly in all possible cases. Not just in a few cases that we have tested, but in all possible cases. And this notion of proof is the key notion here. And this is proof in the most strict mathematical sense of the word, right? Just like you prove Pythagorean theorem, you prove also that your program will terminate under all possible inputs. Now, there is one difference with mathematics, though, and that difference is crucial, that the methods that we are developing here are computer-aided. So these are not proofs that you do with paper and pencil. They cannot be done with paper and pencil because we are talking about millions of lines of code, billions of transistors, right? So humans cannot really manage that. So these methods need automation, and we are indeed using computers to help us do these proofs, or to do them even fully automatically in some cases. And this is also, I find it even philosophically pleasing and interesting, because proof is a highly advanced intellectual activity that humans are able to do, right? And now we are teaching, if you want, in quotes, computers to do these proofs automatically. And we are developing many, many kinds of tools. I will not have time to get into details. They are called model checkers, theorem provers, SAT SMT solvers. So they have these fancy names. All these tools are doing proofs of one kind or another. So thinking as a computer scientist, the compiler has been, the workhorse, the main tool that everybody, I think, knows, even beyond computer science. It's taking a program and it's making it executable so that you can really run it. But now the prover or solver, this device that does automated proofs, is also becoming increasingly important, and I think personally equally important, and often merged. It's under the hood. Many compilers these days include such provers or proof functions under the hood. So you have the compiler producing the executable. You have the prover helping the programmer get their program correct. Now, it's an area that has received a lot of recognition, at least internationally. It has produced many, many Turing Award winners. These are pictures of them that I collected the other day from the ACM website. So Turing Award is the perhaps Nobel Prize equivalent for our field. And all these people have worked in the field of formal methods and recognized for their work. It's also an area that has had impact in the industry. Traditionally, I would say it's an area that has been financed in the old days, 30, 40 years ago maybe, by avionics and defense industry. And these were the only industries basically that had budgets big enough to fund these methods, which are more expensive, or were at least at the time more expensive than just testing. But these days, these methods have become or are becoming more widespread in many other industries, civilian industries. So they are routinely used in hardware industry, electronic design automation, where these days you will find a job title, verification engineer. This is not something that existed maybe 10, 15 years ago. They are becoming widespread in the software industry. This is a quote from a recent book that claims that more than 500 machine years have been used at Microsoft for security testing using formal theorem proving techniques. And it's becoming also successful in somewhat unexpected industries such as cloud computing or online systems. And this is an article that appeared in Communications of the ACM about 2 years ago with title, How Amazon Web Services Uses Formal Methods. And when I looked at this for the first time, I said, hold on, why on earth would Amazon, an online store company, use formal methods? But reading the article, you understand that these companies are developing huge data centers and are developing a lot of software, a lot of distributed protocols, cloud computing, all kinds of systems that run in these data centers. And these distributed protocols are very, very difficult to get right. And you really, really need these techniques to get these distributed concurrent systems correct. And when you look at the article, they make some pretty interesting claims that formal methods can find bugs that cannot be found through any other technique we know of. They are surprisingly feasible and routinely applied to the design of complex real-world software. So it looks like the future is bright for formal methods. However, this is by no means, this is a relatively old field, and there are still many challenges. We cannot claim problem solved and retire, go do something else. This is, first of all, a tough area. I haven't talked about theory here, but this is really an area that requires a lot of mathematical skills, advanced mathematical skills that the software engineers that we produce from our bachelor's degrees, and not just us at Aalto, but universities around the world, typically do not possess these advanced skills. I would say that the problem comes even earlier. The students that come from our schools do not have the required mathematical skills. They take a lot of math, they do a lot of calculus, They do a lot of geometry, but they don't do logic. And logic is really what these things are founded upon. And in the era of computing, I think we really need to look at this carefully and try to teach our children more logic than they are getting right now. Now, this is a nerdy area, okay? We have to face it. We are not as sexy as people who are making cool robots or cool games or cool graphics or cool whatever you have. It's really, we are tool makers. We are not system builders, okay? So we are not building the robot. We are not building the self-driving car. What we are building are the tools that are really, really necessary for the people who are going to build the self-driving car or the robot. Just like you cannot build just about any mechanical thing without a screwdriver, you cannot build these complex systems without such tools. Okay, so these are very sophisticated screwdrivers, if you want. Finally, the problems that we face are fundamental. They are hard theoretical problems that have been around for a while. Nevertheless, we are making progress and amazing progress if you really think about it in making these problems feasible and solvable in practice. Such solving is perhaps a very famous problem. Take a Boolean formula, check whether it's satisfiable. It's a so-called NP-hard problem. It means it's combinatorial, one of the most computationally hard problems in a class of NP-hard problems. Yet modern tools called SAT solvers can deal with this problem in most practical cases, even when the problem has hundreds or even millions of variables. Software verification is another difficult, in fact, it's an undecidable, generally unsolvable problem, yet many practical tools exist that work on real-life software. Model checking, the finite state instance of verification, where you have a system where, in principle, you could enumerate all its states one by one and see if there's something wrong, is plagued by so-called state explosion. The number of states is so huge that you couldn't possibly terminate the exploration in any reasonable time if you go with a brute force method. And yet, again, there are many, many practical tools that are making advances every day in attacking this problem. And the list goes on and on. So high impact in academia, high impact in the industry, important for society, for safety critical systems, and important for education. So let's invest in this area. And it goes beyond software. As I said again at the beginning, it's not just about standalone machines anymore. It's about systems, okay? It's about software and computing embedded into so-called real-time embedded cyber-physical systems, Internet of Things, many, many different buzzwords. The basic methods I believe are the same, so formal methods on larger scale, but again, this is not something that computer scientists can do all by themselves. We need models, we need to characterize the physical environment, and this is not something that we understand. Therefore, the interaction with other disciplines is key here. And by other disciplines, I really mean most other disciplines, even the social sciences, since these systems are going to interact tightly with humans. So I only have one slide about what we are doing at Aalto, and I'm not really going to go through it given the time limits. But I would like to thank here my group here at Aalto, my students, my postdocs, my colleagues here at Aalto and all over the world with whom I'm doing all this work, and thank you all. I will just briefly list, you can go to our website and see some of the things that we are doing here. One of those things is compositionality and abstraction, again coming to what Antti perhaps was saying this morning. When the system enlarges, what do? You try to break the problem into smaller problems. You try to abstract the problem, ignore the the details that don't really matter, focus on the essential things. And we are developing a framework that does exactly that. It's called RCRS, or Refinement Calculus of Reactive Systems. Again, I invite you to take a look at the website for this and other things that we are doing, or contact me if you're interested in learning more about this field. So with that, I will stop here, and thank you all for coming.